All right. Hello, welcome to our presentation of analysis of wireless charging pads. My name is Aniruddha Kailasam,
And my name is Huang Fan.
and yeah, let's get started. So first thing, let's describe what our actual physical problem is here. So we decided to model a wireless, kind of like those circular wireless charging pads, as a 2D transient heat transfer problem. So as you can see by the figures, first we decided to model the heat gen, which is basically the induction coil in those chargers over a specific area within the circle, which is denoted by this right here. You see the shaded area. And the outer edge, we made it so it's exposed to heat transfer. So there's like a convection condition on the circumference. We also made a couple assumptions. The first being that there's negligible heat transfer through the thickness of the actual charger. This allows us to maintain the model as a 2D model. We also kind of created our own material properties where it made it easier to model, so the flow went through the material more effectively, and it was easier to see. Yeah.
Next, so in order to reduce the computational time for the actual governing equation, only a quarter of the circular plate had to be modeled due to symmetry. So as seen on the governing equation on the left right here, since the domain is in like a circular shape, the governing equation can be described using the polar coordinates, and that could also be used as the computational domain. And furthermore, the boundary for the problem is as follows. For theta equals 0 and theta equals pi over 2, there will be no normal heat flow through these boundaries. So therefore, there's no heat transfer through those boundaries. And also at r equals 0.05, there's also no heat flow in order to model the center of the circular plate. And finally, at the outer edge of the domain, since it is exposed to ambient air, there's going to be a convection condition for this bound. It is also assumed that the charging pad is initially off, so therefore the initial temperature over the entire domain is equal to the ambient temperature. And also for the domain, since the charging coil only spans from the center to the halfway point, so therefore the heat generation only occurs from 0.05 to 0.5. And as you can see on the figures on the right, this is how the domain will be discretized for the two numerical methods. For the finite volume methods, the nodes will be in the center of each of these finite domains. And however, for the finite element methods, the nodes will be on the corners of the finite element domains. So these two methods will be used to solve the problems, and their accuracy will be compared. So firstly, the problem will be solved using the finite volume method. So for the finite volume method, the governing equation must first be integrated over the entire area, over the entire finite volume, as seen in the figure on the right. So as seen in the figure, the compass notation can be used interchangeably with the indices in order to discretize the governing equation after the integration process. And from there, a node numbering scheme can also be used with the indices in order to organize the rows and the columns in the A matrix and the B vector. When deriving these governing equations for the finite cells, care must be taken for the nodes on the boundaries, since these nodes have the boundary conditions. So the Newman boundary conditions is applied for all the edges that has the node normal flow boundary conditions, which can be seen on the figure on the right. And also the convection boundary conditions can be applied for all the boundary cells on the right of the domain. And you can see it from this figure right here. So after all the governing equations are derived, it can be placed into the A matrix and the problem can be solved using an implicit method. So secondly, the problem can also be solved using the finite element method. So as seen on the left right here, the governing equation is written in the matrix form for easier mathematical manipulations. So for the finite element method, the method starts from the strong form of the equation, which is the original PDE. And from there, the equation will be multiplied with a weighting function, and it will be integrated over the entire domain. After that, using methods such as integration by parts and the divergence theorem, the weak form of the equation can be derived. And you can see it on the bottom right here. After the weak form has already been derived, the temperature over the domain can be approximated as a function of the temperatures at the nodes using a bilinear mapping shape functions. And for each of these individual elements, four different shape functions can be derived. And also the gradient of those shape functions will also be used in order to discretize the governing equation. And after that, the discretization can be placed into the governing equation, the weak form of the governing equation as shown above. So as shown here, this box shows the discretization of the left-hand side of the governing equation. And one thing special here is the discretization of the time difference term. The time was discretized using a backwards time difference, which would allow the method to be solved implicitly. And at the box at the bottom here shows how the right-hand side can be discretized. So those terms can be substituted in the original weak form of the governing equation, and from there, the equation can be reorganized and to find the local stiffness matrix and the local right-hand side matrix. And for a quadrilateral element that we implemented for interdomain, the local stiffness matrix can be seen right here as a 4x4 matrix, and the local right-hand side matrix will be a 4x1 vector. And after that, those type of the local matrices will be stamped onto the global matrices, and the solution can be solved. So this slide shows the solution process of the two numerical methods. The two methods are very similar in the solution process. However, the only difference is the construction of the matrices that represents the systems of equations for each of the domains. And after that, the analytical solution can also be used as a validation tool to validate like the two numerical methods that were used above. So in order to use the analytical solution, there has to be two assumptions. The first one is there is no heat flow in the circumferential direction, and also the problem has already reached steady state. So the general solution for the problem can be solved using the governing equation on the right here. And then after that, the boundary conditions and also the continuity conditions can be applied to find the constants for the general solution. And that will result in the particular solution that can be seen on the bottom left right here.
Thank you. So for the actual ANSYS, we decided to use ANSYS to simulate and model the problem as well. Basically, the procedure and process of how we went about doing that was first we modeled within ANSYS as a 2D model, right? And then we created a modal mesh, which can be seen here on the right. And then on the left, we also integrated and implemented the boundary conditions that were mentioned and used for our previous examples in analysis, right? So as you can see here, they're labeled A through C. So if we start with the A condition, it was basically adding an insulation to the center of the charging pad. And then B is this pinkish mesh that surrounds that inner shaded region. That's the actual internal heat generation. And then we implemented a C boundary condition, which was the convection that occurs at the boundary of the charging pad, right? So once we did that, we were able, right here you could see once everything was modeled, that the transient solution for both the finite volume and the finite element, which are these two, are very similar to the ANSYS solution, right? The convergence time for all three methods actually occurs around the same time, which is about 1.5 seconds, okay? And in this right here, we see that the steady state for the two methods, again, were very similar. And for the finite volume method, the contour area is on the left, so this smaller region right here, and then on the right are smaller because they're closer to the boundary nodes. And additionally, for both the solutions, the contour lines at the perpendicular, so right here and right here, are are have a non-normal flow condition, so they're basically, I believe that they're zero, and the maximum temperature is at the center and it extends outwards. And if we go on, so here we see all the methods kind of graphed together. So we have ANSYS, analytical, finite volume, and the finite element. And as you can see, the ANSYS and the analytical and the finite element are all very close, are very similar to each other. For the finite volume, there is a discrepancy, and that's due to the model, because it's difficult to model the interface between the two domains, being the internal heat generation and then that outer ring where the heat transfer occurs. But the discrepancy is only about 0.5%, which is able to still be considered as accurate, right? So, and here we see that both the finite volume method and the finite element method have a first order accuracy. And this is just to, visually see that as well, right?
Yep. And now is the conclusion for the presentation. So the heat transfer problem was solved numerically using two different methods, which is the finite volume method and the finite element method. So the two methods have differences, basically on like how the governing equations are treated and also how the matrices are constructed. From the results, it can be seen that both methods provide very accurate results. The transient solutions were very similar to the ANSYS simulation, which was shown above, and the error was very small compared to the analytical solution. And finally, it can also be seen that the finite element method had a higher accuracy.
Right.
And that's the end of our presentation. And thank you so much for listening.
Thank you.